seems like we're on a trend of 1 week off, 1 week on, right? Because we had the snow days and then a week of class and then spring break. So we'll be here this week. Who knows what's going to happen next week? Another freak snowstorm maybe? Who knows? We can only hope. Your next homework assignment is due on Tuesday the 31st. That's homework 9. That's also on the modified class schedule that I handed out. All the homework assignments and all the project due dates are incorporated onto that double revised because it's the second revision of what I gave you. Looking a little bit further than next Tuesday, the network sizing draft is due on Thursday the 2nd. And I'll show you a picture of a map just to set the stage for a discussion on that here in a second. And finally, looking a bit deeper into the future, April 16th. Anybody remember what April 16th is? Hydraulic Jump Day. So remember to order your wigs, start picking out your blue outfit, composing your poems, thinking about what's appropriate Hydraulic Jump Day songs, and all of those important things so that it can be a special day for us all. All right. Today we're going to be talking about total energy, specific energy, and critical flow. I wanted to point out just a couple more things about the design project. You know, we're going into the WaterGems phase, and I sent out these links previously, but if it's been a while since you used WaterGems and you just don't remember what buttons do what activities, or maybe you've never used it before, here are a couple of demos from what we did in fluid mechanics to bring you back up to speed on the basics of WaterGems. And then one other thing that I provide is a link here to a PDF creator. And what that allows you to do is you can print to a PDF. Instead of printing to paper, you can print to a PDF. And it's useful to upload your maps as PDFs in MU Online. So I'll talk a little bit more about how to submit your network maps. But if you don't already have a PDF creator, that one's free, and it's good. All right, so here's an example of an annotated map that you're going to need to submit next Thursday. Was it next Thursday? Yeah, next Thursday when your draft submission's Thursday, April 2nd. Okay? So what's good about this map? You tell me. I know what I like about it. What do you like about this map? Okay, all right, yeah, that's a good point. I wasn't going to mention that, but yeah, this is H, which is the golf course, housing project. So all of the external flows are labeled. You know, here's a demand. I think that if I'm remembering correctly, this junction feeds into the southern loop. This one feeds also into the southern loop. Now this was from a previous year when the students had to put pipes between all of the junctions. You have some further flexibility where, for example, maybe you could cut this pipe out because, you know, the water could come in from other directions. So yours doesn't necessarily have to look like this in terms of where the lines are, but what I'm talking about is there's some nice things as far as the annotations go. Annotation is labels, and so you'll notice that it's showing the pressure at each junction. It's showing the demand that's coming out at each junction. And some of these junctions don't have flow coming out of them. They're just where the pipe changes direction. There's the flow through the pipe is marked, the length of the pipe, the diameter. You're actually going to submit 2 different maps. Does anybody remember what the 2 different maps are that you have to submit? They're of the same network, but just under different conditions. Right, exactly. So elaborate. What does that mean? Good. So it's like a snapshot of the network when no one's using any water. And at static conditions, when there's no demand, what do you expect the pressures to be? High pressure or low pressure? High pressure. Why will the pressures be high at night? There's no velocity through the pipe, therefore there's no energy losses. So everywhere in the network is going to have the highest pressure it's going to see based on how high up on the hill the tank is and the elevation of that junction in the network. Okay, so that's the static condition. And the peak condition is, you know, whatever you determine is the design flow rate at each of these either loop locations or external locations. Which is this? Is this the static or is it the peak? That's right, it's the peak, because we see water is flowing through the pipes, and then the other sort of clue is that the pressure is nearing the lower limit. What's the lower limit for our design? 240, I think. 240. So the closer this student gets to 240, the happier I am. That's evidence of optimization. If I look around and the pressures are in the 400s and the 500s, I start to say, oh, this student didn't make the pipe small enough. You know, you could have made that pipe a little smaller, and it would have reduced the pressure a little bit, but it wouldn't have taken the pressure down below the limit. And so that pipe is unnecessarily large. Shame on you, student. Right? That's optimization, is go save your client money by making the pipe smaller until the pressure, you know, ideally you'd have 241 kPa at every junction. But you can't really achieve that because there's increments of pipe sizes. You're not going to be able to put in a 203 millimeter diameter pipe because they don't make a 203 millimeter diameter pipe. They make 200, 225, 250. I think I marked the pipe sizes on the handout. All right. How would I know if the reservoir is too high up on the hill? You know, like when I'm grading your work, how can I look at your maps and know if the reservoir is too high? What's that? Okay, above the range. On which map? Static, right. So the static map is when there's no flow through the system, and so that's when you're going to see high pressures in the network. And so if you're doing your analysis where all of the demands are set to 0, that's what you have to do to analyze it at static conditions, and you're seeing like 900 kPa, that means don't change the pipe sizes. If you see any places over 850, that means you have to bring the reservoir lower down on the hill. Yes? You need to type that into the computer, right? You don't need to include it as an annotation, though. But you do need to tell the computer what's the elevation at the junction so that it can take that into account when it's calculating the pressure. Other questions? This is the fun part of the project. Funnest, I guess. It's relative, right? It's like as fun as a root canal. But. All right. Well, today we're going to talk about specific energy. And specific energy is calculating the energy relative to the channel bottom at one point in particular. So let me compare the difference between total energy and specific energy. Okay, so here's the channel bottom, and here's the water surface, and then here's the energy grade line. So we call this EGL, or like the total energy. And sometimes what we do is we pick a datum, a horizontal datum, and we would measure our energy relative to that datum. That's kind of what we've done in the past, is we've said, here's some horizontal plane, at any point, you know, here's location 1, I want to find out what is the delta Z, the Y, the V squared divided by 2G, and that's what we'd say is the total energy at this location. By contrast, specific energy is only considering how much energy is there above the channel bottom. So we're neglecting this delta Z, and we're just saying at any particular point, let's add up the depth and the velocity head that's above, you know, between the water surface and the energy grade line. So here we're saying E, meaning specific energy, is the depth and the velocity head. And we've made the typical substitution in this lower formula. Instead of having it in terms of V, we have it in terms of Q. Because sometimes when we don't know the depth or the velocity, it's more convenient for us to express this in terms of flow rate, which may be known. All right, so just as a thought exercise, if we had a channel that's 4 meters wide like this, and let's put 10 cubic meters per second of water through that channel. So if we change the slope, that's going to affect what the depth of the water is. And so how many different combinations of velocity and depth are there that will convey 10 cubic meters per second through the channel? How many different combinations of velocity and depth will there be? Is there only one possible velocity and depth? More than one? It's an infinite number, really. Because as you make it just a little bit steeper, then the depth goes down and the velocity speeds up, but it's still the same 10 cubic meters per second going through the channel. And so that's what I'm illustrating here. I've put together a table that shows, let's just pick a lot of different combinations of, for the same flow rate, if we want to pick a certain velocity, what would be the corresponding cross-sectional area and the corresponding depth? And so, I've calculated a bunch of areas there. What would you do to find the area here? Actually do that calculation. Calculate the area, the depth, and the energy for the three rows that have those green arrows next to them. Of course, you can collaborate with a classmate there, but calculate A, Y, and E for those three different rows. All right. You already know I'm just a little bit obsessed with Excel, and maybe I'd throw in a table like this just because you can do it easily on Excel. Maybe that's the case, but actually there's a deeper meaning than that. There's a bigger reason why I asked you to do the calculations, because I want you to remember this table. We're going to use this table a lot of times in the coming weeks to answer questions. It's actually, when you graph it, kind of like a Rosetta Stone to solving problems that have to do with energy flow in channels. So there's definitely some meaning here. And we'll take the next few minutes trying to interpret what is the meaning of this table. And the first thing I want to draw your attention to is what depth has the lowest specific energy. So remember this last column E, that's specific energy. And what it starts off with is, to get the water moving 10 meters per second, we're going to have a pretty high velocity head. When you've got a lot of velocity, you've got a lot of velocity head. There isn't much depth, but this E, which is specific energy, it's the sum of two kinds of energy. It's the depth component, which we could think of as maybe a potential energy, and then there's the kinetic component of that energy, which is the velocity head. And so most of the energy in this first row is in the form of the velocity, 5.3. But then the specific energy is going down. So it's going down because our velocity is decreasing at a faster rate than the depth is increasing. So compare this first row to the second row. We got a little bit more depth on the second row when we went from 0.25 to 0.31. So you'd say, well, you're getting a little more of the Y, but you lost a lot of the velocity head. So that's why the sum of the specific energy went from 5.3 down to 3.6. Okay? And it keeps going down until, now this is a pretty strange velocity. I don't know why I asked you to calculate the components associated, but it just miraculously turned out that that velocity corresponds to the lowest specific energy. And so there's something unique about that depth, the depth that gives you the lowest specific energy. And we'll talk about what's the significance of that. First, a couple of graphs. And you'll need to make graphs like this for future homework assignments. And so the way you make a graph like this is, first you start with a table like this. When you have a homework assignment where you're having to draw the specific energy diagram, you won't be given a variety of a bunch of different velocities and depths. You'll just have to say, I'll start with a big depth and go through a little depth, and I'll get like a whole variety of specific energies. So you'll make some table like this, and now this is a graph of flow depth versus flow velocity. And this isn't too interesting, but let's just look at it for a second before we move on to the really interesting graph. So here, the flow depth is high, but we have a low velocity. Each one of these combinations gives us the same flow rate. Remember, these are all for the same 10 cubic meters per second. So you can have 10 cubic meters per second either because the water is deep and moving slowly, or you can have it that the water is shallow and with a really high velocity. But you could make a curve like this for any combination of channel geometry, any flow velocity that you want. There's nothing unique about this form of a graph. But what's more interesting for understanding what's happening with the flow is to graph specific energy on the horizontal axis and then depth of flow on the vertical axis. And why that's interesting is because what you can see is that for each specific energy, there's two different flow depths. And so let's go back to the table that this is based on. This curve here, it is, you put E on the horizontal axis and Y on the vertical axis. And so what it's saying is there's two different depths that go along with the same specific energy. Let's just use 2.5. So 2.5 is going to be a depth, if our specific energy is 2.5, that would be a depth between 1.25 and 2.5. So it's going to be closer to this depth because we would interpolate between the two. There's some other depth that has the same specific energy. It's the depth that's between these two. And so this curve is showing, continuously that for a certain amount of specific energy, there's two different depths. But what we noticed is there was this one depth that had the lowest specific energy, and this is associated with conditions that are called critical conditions. Minimum specific energy and critical depth. And you'll remember that in one of your homework assignments you had to classify whether the flow was supercritical or subcritical according to the Froude number. This is a graphical way of assessing whether the flow is supercritical or subcritical. And the dividing line is the critical depth, which is the only depth here that has just the only energy that has a single depth. Every other energy above that has two possible depth combinations. So the thing that controls what depth it's going to flow at, all the flow conditions contribute to it, like the roughness of it, the geometry of the channel, but ultimately it's the slope that dictates whether you're going to have a shallow depth and high velocity or a deep depth and a slow moving velocity. If you think about different rivers that you've seen, if you go into the mountains where there's really high slopes, that's when you see rapids and fast moving water. And when you go to flat places like next to the Ohio River, the slope of the water there is very low, and that water is moving relatively slowly because of the mild slope that it's got. And so these different specific energies are determined by the different channel slopes that a certain amount of water is flowing through. So it's called alternate depths. When you have a certain specific energy and there's two different depths that the water could be flowing at if it has that much energy. The water can have a certain amount of energy and pick one of two different flow depths. So we'll talk more about critical flow. And that dividing line of the minimum specific energy is the critical depth. And so if you graph it and you find the lowest specific energy and then you take it over to the y-axis, that depth there happens to correspond to, if we go back to the table, I think it was 0.861 was the lowest specific energy. That's not the lowest depth, it's just the depth that corresponds to the smallest specific energy. So 0.861, and we go over here, looks like it's about 0.8. We can't really visually determine more accuracy than that, but we can by doing the calculations. When you have a channel that's rectangular, then the top width is always just going to be the same as the bottom width of the channel is. But if you have a trapezoidal channel, then the top width is changing depending on how deep the water is. So, here in a rectangular channel, it's easy to know what the top width is because as the water gets deeper and deeper, the top width stays the same. But in a trapezoidal channel, as the water gets deeper and deeper, the channel is getting wider and wider at the top. And so we have a special name for the top width that's corresponding to critical conditions, and we just give it T sub C. That means the top width when the conditions are critical. So when you have Y sub C as your depth, then the top width is T sub C. Now here's the Froude number equation. You've seen this before from that previous homework assignment. And the dividing line is 1. Any Froude number greater than 1 is supercritical flow, and any Froude number less than 1 is subcritical flow. So here is that when Froude number is less than 1, flow is subcritical. When Froude number is greater than 1, flow is supercritical. But we can also diagnose whether the flow is supercritical or subcritical according to the flow depth and how it compares to the critical depth. So let's go back to the graph just briefly. If the water depth is 1.5, that's above the critical depth. Now this is a little counterintuitive, so this is like on the top 10 list of commonly made student mistakes. Any depth greater than the critical depth gives you subcritical flow. And why that's counterintuitive is because sometimes students think, well, deeper must be super. But no, it's the other way around. If you've got deep water, that means the velocity is low. And so it's subcritical. But if you've got shallower water, shallower depth than the critical depth, that means that you're going to have high velocities. And so that's associated with supercritical flow. So if I told you that we had this channel and we had 10 cubic meters per second and the flow depth is 0.5 meters, then you could just look at this and see 0.5 meters is going to be less than the critical depth. Therefore, at 0.5 meters, the flow conditions would be supercritical. So you can use this curve to diagnose the flow regime and know whether the conditions are supercritical or subcritical. That's one of the uses of this curve. Any questions so far? All right. I think we've also talked about hydraulic depth before and how it's the ratio of the cross-sectional area to the top width. And we'll get back into the hydraulic depth a little bit further, talking about wide channels. All right. So if we have 10 cubic meters per second and the depth is 0.25, use the graph to tell me, is it supercritical or subcritical? We can tell just by looking. So if the flow depth is 0.25, for this chart, is the condition supercritical or subcritical? It's supercritical, right, because remember, it's any time the water depth is shallower than critical, and this is the same curve that we've been using so far today. This is showing the critical depth is at 0.86. And so for a flow depth of 0.25, you've got supercritical conditions. And by contrast, a depth of 1.25 is going to be above that critical depth, and so it's going to be subcritical. So what I'd like you to also try is the other way of verifying that. Calculate the Froude number for both of those. And Froude number isn't only used to diagnose super versus subcritical. It has other importance as well. But in this case, it'll validate what we can know from the graph. And so calculate the Froude number for both of those flow conditions. Rectangular channel makes it easy. I love to see it when you're punching numbers into your calculator. It's a beautiful sight. Here's my calculations up on screen there. So it's confirmed, the graphical solution didn't lie to us, that we have supercritical conditions when the depth is 0.25. We can know that either by looking at the chart and seeing that that 0.25 is less than the critical depth, which was 0.86. That's the graphical way. Or calculating the Froude number, since it's greater than 1, that also tells us it's supercritical flow. And the opposite is true for the depth of 1.25. It's subcritical because the Froude number is less than 1. And subcritical because the flow depth is greater than the critical depth. We'll also use it when we are dealing with hydraulic jumps. So this isn't the only time. Froude number is useful for hydraulic jumps. Other questions? All right. This is actually pretty deep stuff today. We're going to be like really relying on this to do some complicated stuff. So if this is just seeming really natural to you, that's a good sign. It means good things are going to happen in the coming weeks. Okay, I mentioned that we'd get back to hydraulic depth. And remember that hydraulic depth is kind of a way of taking a non-rectangular channel and finding out what would the equivalent depth be if you transformed it into a rectangular channel. So take this trapezoidal channel just as an example here. You know, we've got side slopes where the horizontal to vertical is t to 1. That's how we define the side slopes in the trapezoidal channel. And you'll notice that the Froude number equation here can be in terms of the flow rate, top width, and area. Or if we happen to know the hydraulic depth, d, then we can simplify it just by putting in the velocity, and you know, we don't have to put in a separate t parameter. Well, if you have a rectangular channel, what's the hydraulic depth of that? Hydraulic depth is going to be the area divided by the top width. And for a rectangular channel, the area is just t times y. And so t times y divided by t, if you just have a rectangular channel, then d equals y. So that makes it pretty easy. That changed the Froude number. Froude number squared for a rectangular channel is just the velocity squared divided by gy. So that's pretty straightforward. And there's kind of a, this isn't on your slide. You'll need to mark this in the margins. I intentionally hid this, I think, right? This little part doesn't appear in your slides. All right. When a channel is very wide, then you can assume that the hydraulic depth is equal to the flow depth. And this is kind of one of those things that requires a little bit of interpretation, but just as a rough guideline, what we mean by a very wide channel is one where the width is 20 times greater than the depth. And let me just illustrate what I mean by that. Here's a rectangular channel. This channel's pretty wide. You can tell just by looking at it here. You know, we've got some flow depth and we've got some bottom width b. This is rectangular. Here's trapezoidal. All right. So what I've said here is that for a very wide channel, the hydraulic depth is also equal to y. Now look at these drawings. What I'm saying is, if the channel is very wide, you can treat it as though it's rectangular. Why do you think we're allowed to make that assumption, or that simplification? Yeah, it doesn't matter. Look at this. This tiny little flow area over in the corner sides, it's basically negligible. And so it makes our calculations a lot easier if we can just say, well, you know, the cross-sectional area doesn't really change too much as a function of depth because of, you know, the top width is getting wider. It's getting a little wider, but minimally compared to the fixed bottom width. And so this rule of thumb is that when you've got a very wide channel, it simplifies a lot of the equations, but you always need to double check whether the channel really is very wide after you invoke that assumption and the resulting simplifications it enables you to utilize. All right, so a big star and warning next to that. Don't abuse the very wide assumption because it can bite you if your channel's not very wide. All right, so alternate depth is the name that's given to these two different depths that have the same amount of specific energy. So what is the specific energy when we have a depth of 0.5 meters? All right, let me do that calculation up here on the board. Let's say we've got, for the flow conditions of 10 cubic meters per second, B is 4. What is the specific energy when we've got 0.5? Okay, specific energy formula is E is equal to Y plus Q squared divided by 2GA squared. And we're going to do this for, we've got a 4-meter wide channel. We have some depth Y, and we're going to see for Y equals 0.5 meters, what is E? And we've got Q is equal to 10 cubic meters per second. All right, so E is going to be that depth of 0.5 meters that's given, plus our Q squared, so that is 10 squared divided by 2 times 9.81 times the area squared. Area is going to be 4 meters times 0.5 meters. And we're going to square that. Okay, the E is 1.774 meters. It has units of length. So what is the alternate depth to 0.5 meters? Graphically it's easy, kind of. You don't get a lot of precision in the graphical method, but we can get a rough idea of what the alternate depth is going to be. Look at that specific energy diagram. Sometimes this kind of a diagram is abbreviated SED. I think that's also the abbreviation that's given to people who get depressed when it's like wintertime because they don't get enough sunshine. Seasonal affective disorder. But we're talking about specific energy diagram here, not that. So what's the alternate depth to 0.5 meters? Look at the graph, the SED, and tell me what's the alternate depth to 0.5 meters? Yeah, approximately, just roughly when we've got 1.77, 0.5, yeah, 1.25 or so. So let's just put our guess is it's maybe around 1.25 meters is what you said. How can we find the real alternate depth? Any guesses? That's right. It's exactly right. So 1.774 is equal to Y, some unknown depth, plus same flow rate, so it's still going to be 10 squared. 2G remains unchanged. And then our area, it's still going to be 4 meters. It's going to be 4Y squared. And solve for Y. Okay, so it's going to look like this 10 squared is 100. So we'll have 1.774 is equal to Y plus 0.3186 divided by Y squared. We can rearrange that to look like this. Y cubed minus 1.774 Y squared plus 0.3186 is equal to 0. Can you solve for roots on the Casio? Okay. Find the roots of this equation. With any luck, one of those roots will be 0.5 meters. No. What we'll do is we'll eliminate the depth that we've already got. There will be 3 possibilities. I think 1 will be negative, 2 will be positive. Yeah, okay. All right. So we can eliminate the negative root. The alternate depth is not some negative flow rate where the water is below the channel. And we're trying to find what's the alternate to 0.5. Well, 1.66. Our guess is 1.25. Let's take a second look at that. So 0.5 up here. Okay, yeah, it is 1.6. So that's a good illustration of why maybe you'd want to not rely on the graphical method and do the calculations instead. Okay, so this is our alternate depth. Who can rephrase, what does this mean? Who cares? What's the significance of 1.66 meters compared to 0.5? Say it again. Oh, very good. Yeah, I hadn't even thought of it that way, but one of them is the supercritical depth. One is the subcritical depth associated with the same amount of energy. That's right. So this is the subcritical depth, and this is the supercritical depth associated with the same energy level. So if the water has a certain amount of energy, it can flow either shallow and fast, or it can flow deep and slow. And these are the 2 different depths that it can flow at and have that certain amount of energy. Well, what we've done so far is we've neglected any energy losses. And so when you're thinking in terms of more efficient, you're thinking like, what if there are energy losses? We'll actually get to that in a couple of classes, like where we'll have the channel getting narrower or wider, and this will tell us what to do. Yeah. So I'm glad to see that you're thinking ahead on that. Other questions? All right, so this is basically just assuming that the water has a certain amount of energy, and we want to know the 2 different flow depth possibilities. And the reason why we do this is that this kind of diagram is very, very helpful. Let me just show you a quick preview of the application. Let's say that you have a channel, and the water is flowing. It's uniform flow and it's steady. So what do we call the depth when you have uniform flow and steady conditions? Do you remember that? Close. Normal. Very good. Okay, so normal depth. Normal depth just means normal conditions. There's nothing out of the ordinary. It's in equilibrium with the channel resistance, with the slope. Just everything's in equilibrium and everything's normal. You've got the normal depth. What equation do you use to calculate the normal depth? What's that? No, there's one equation that you can use for any different channel geometry. There's a name. It's a person's name. Manning's. Yeah. Okay, so normal depth, use Manning's equation. Okay, it's easy. But how often are conditions normal? Now, how often do you have a channel where it's just a continuous, steady slope with no bumps, no obstructions, the channel isn't getting narrower or wider, you know, it's pretty uncommon. The only case where you'll have one is an artificially engineered channel with no changes in geometry. Most of the time, conditions aren't going to be normal. And so we use this when there's something like, an obstruction. When you've got like just a block of something in the way. Well, as the water approaches that, it's going to respond to that obstruction. And it actually does some pretty weird things. You'd expect maybe it's going to get deeper, but in reality, sometimes the water will get shallower over the obstruction. Sometimes it'll get, depending on the height of the obstruction, if it's pretty tall, well then, in that case, the water's going to have to get deeper before it can flow over the obstruction. And so being able to calculate specific energy is going to be the key to our analytical method to know how is the water going to behave in non-uniform conditions. When we've got an obstruction, is it going to get deeper over the obstruction, shallower, or what if, now this is a top view here, what if we have the channel like this, here's the water flowing this way, and then it translates into a narrower channel. You know, how is the depth going to behave when all of a sudden the channel's getting narrower? You might think, well, it's going to back up. You know, it's blocking the flow somehow. But it's that same kind of thing where it can be unexpected. Actually, the water might get deeper or the water might get shallower in response to a transition like this. And we're going to use calculations of specific energy to help us understand how the water is going to react to non-uniform conditions. The other key is whether conditions are supercritical or subcritical, because whether it gets deeper or shallower in large part is dictated by whether it's supercritical or subcritical. And we'll get into all of that, but I just wanted to give you a glimpse of why the specific energy calculation is so important and why it's important for you to be able to generate a specific energy diagram. All right, I think this might be the last slide. No, it's not. False alarm. All right. Critical conditions is just the specific energy that's associated with critical depth. And so if you look at this chart here, the specific energy diagram, you notice that every point on this diagram has some slope except for the critical depth. The line is just straight up and down. And so if we go through the mathematical derivation of, if you take the derivative of energy with respect to y, so dE dy, then this specific energy formula changes to as shown, and we can rearrange that based on the assumption that if you have critical flow, meaning that for every change of depth, dA, the incremental change of depth dy for a certain top width, dA is the depth dy times t. And so if you have a really, really small dy, the top and the bottom have essentially the same length. And so you're using some top width t, and you have dE dy is equal to 0. That's where this formula for critical conditions comes from. You can find out what is the depth for critical conditions. You can solve for the critical depth by using this formula, in other words. So here, if we move the, if we say the critical depth, yc is the critical depth, that gives us the AC is going to be the width of the channel times the critical depth. The top width is just T sub c is the top width when we've got critical conditions. This is going to be always true regardless of what the cross-section looks like. So for a rectangular channel where we've got 10 cubic meters per second and the top width when you've got critical conditions is 4 meters, find yc. This is going to be that same 0.86 that we saw earlier when we were putting together the calculations with the table. This is just showing how you can find what is the critical depth, because remember, you can diagnose whether conditions are supercritical or subcritical either by the Froude number or by comparing a certain depth to the critical depth. So this is how you find the critical depth. we can rearrange this top equation where it's q squared divided by g is equal to a sub c to the third power t sub c. Well, we just rearrange that to q squared divided by g is equal to 4 times the critical depth, because this channel is 4 meters wide, and we cube that. And then we have the top width at critical conditions. We can rearrange that to the critical depth is going to be t sub c times q squared divided by g to the 1/3 power times 1/4, since it's a 4 meter wide channel. And now if we substitute in the actual values that we know for this, it's 4 meters wide times 100, which is q squared, divided by 9.81, which is g. Take that to the 1/3 power times 1/4, and that's 0.860 meters. And so that's the critical depth. And any depth that's larger than the critical depth is subcritical conditions, and any depth that's less than the critical depth is supercritical conditions. All right. Some of our calculations are a little bit easier if we have a rectangular channel compared to if it's trapezoidal or some other shape. In order to use that simplification, we have to introduce a definition that's called flow per unit width. Lowercase q is the flow per unit width. And so just as an example, if you've got q is equal to 10 cubic meters per second, like we've been having with this recurring example, and the channel is 4 meters wide, so b is equal to 4 meters, then lowercase q is q divided by b. So what we're saying is 10 cubic meters per second divided by a channel width of 4 meters. The flow per unit width is 2.5 meters squared per second. That's the units of it, is meters squared per second. So it's how much flow we're getting for every 1 meter of width in the channel. It's easy to calculate the critical depth when we've got this formula, because the flow per unit width is giving us a simplification here. So critical depth is 2.5 meters squared per second. Square that, divided by g, 9.81 meters per second squared, and take all of that to the 1/3 power, and then the critical depth is 0.860 meters. So this is a little bit easier than this first formula. This first formula is always valid. So make this note, always valid. Meaning always means regardless of what the shape of the channel is. And this formula, where it's lowercase q squared divided by g to the 1/3 power, only for rectangular channels. All right, so this is the last example for today. A trapezoidal concrete channel, a bottom width of 3, side slopes of 1.5 to 1, and it's carrying 186 cubic meters per second. What we want to do is find the critical slope that is going to cause the critical depth. So this is actually going to be a two-step process in this example, because first of all, we're going to need to express everything in terms of an unknown depth y sub c, and then we're going to have to use Manning's equation to actually solve for, based on that y sub c, the slope that causes it. Now, these formulas here for T, A, wetted perimeter, W, this is from that table 10.1. This is only valid for a trapezoidal channel. You know, those formulas aren't valid for other shapes. Okay, so if we have this, then we're going to have Q squared times T divided by G A cubed is equal to 1. Okay, so if we put in what we know, this is going to be 186 squared times T. Now, we only know T in terms of the bottom width, which is given, the side slopes T, which we do know, but we don't know Y. So it's going to be 3 plus 2 times 1.5, which is the side slope factor T, times Y, divided by G, which is 9.81 times 3 plus 1.5 Y times Y, and all of that is going to be cubed, is equal to 1. Okay, so I've substituted in this formula for T in the top, this formula for A in the bottom, cubed, and where I know the bottom width is 3, I've put in B equals 3, and for T is equal to 1.5, I've put that in. But for this formula, basically what we're going to try and solve, we're saying is equal to 1. That means critical conditions. When this formula is equal to 1, what we're solving for really is the critical depth. Okay, so y sub c, if you put that into your calculator and solve, y sub c is going to be 4.121 meters. It's the critical depth. So now the reason why Manning's equation is on the screen is what this is ultimately asking is what slope will cause the flow to go at the critical depth. So that's when we rearrange Manning's equation. You see it in its normal form there. We can arrange it in terms of S. Manning's equation looks like this. S is N times Q divided by A, hydraulic radius to the 2/3 power, and all of that is squared. So we've just rearranged this to solve for the slope that is going to give us this critical depth. Okay, so we need to know some of the shape factors here. For example, the wetted perimeter, P, is going to be 3 plus 2 times the depth, 4.121. And we also need to calculate the factor W. W, remember, is based on the side slopes. So it's 1 plus 1.5 squared to the 1/2 power. So W for this is 1.803. Okay, so then we use that W factor when we're calculating the wetted perimeter. So 1.803. The wetted perimeter is 17.858 meters when the water is flowing at the critical depth. Likewise, we can calculate the cross-sectional area when the flow is going at the critical depth. 3 plus 1.5 times y, which is 4.121, which is the flow depth, times 4.121 gives us the cross-sectional area is 37.837 meters squared. And then, of course, the hydraulic radius is area divided by the wetted perimeter, and so that is 37.837 meters squared. divided by 17.858 meters. So the hydraulic radius is 2.119 meters. Okay, so now we go back over here and we substitute in everything that we know and try and solve for what slope is going to cause that flow condition. So it's going to be the n value for the roughness of this concrete channel. We're going to use n of 0.013. The flow rate that we know is going through this channel is 186 cubic meters per second. The cross-sectional area, 37.837 meters squared. And then the hydraulic radius of 2.119 meters. Take that to the 2/3 power, and then all of this squaring it. The slope that we'll get is 0.0015. So why will the water be at this critical depth? It'll just be at that depth because the slope that causes that depth happened to occur in the channel. What if the slope was steeper than that? Would the flow be supercritical or subcritical? If the slope is steeper than this, it'll be supercritical because the water will be moving faster velocity, and therefore the conditions will be supercritical. All right. One last thing. There is an engineering graduate student who's working in transportation, and I think some of you may have already taken a survey that has to do with distracted driving, and some of you haven't. Raise your hand if you haven't taken the distracted driving survey yet. Okay, I'm going to pass that down. It's about how many times a day you text while you drive and so forth like that. So raise your hand if you haven't got it yet. All right, 3. It'll just take a moment. Fill them out, and then when you're done, you can bring it to the front of the class. Everyone else, that's all we've got for today. I will see you on Thursday. You need one? Yeah, I'm sorry. All right. My spidey senses tell me that there could possibly be a quiz on Thursday, so we'll have that to look forward to. All right. Have a good day.